Chapter 14, Transformations. Today we're going to cover Section 14.1, Mappings and Functions. Objectives for today will be to recognize and use the terms image, pre-image, mapping, one-to-one mapping, transformation, isometry, and congruence mapping, and also to recognize the properties of the basic mappings. First two words that we need to know is pre-image and image. And a pre-image is just the original figure. So if I look over to the right, this triangle that I see I can call the pre-image. If I do something to it, either rotating it, flipping it, or just sliding it over, this new shape that I have would be called the image. So original shape is the pre-image, the new figure is the image. Next term we have is mapping, and it's a correspondence between sets of points. So to the right I can see if I'm given a certain x value, it gets mapped or turned into a new value. A function is a correspondence between sets of numbers, and it's sort of the same thing. The numbers you can see go from -1 to 2, 0 to 2, 1 to -3, and so on. So a mapping is the actual points, so you can think of them as being on a number line per se, and the function is just dealing with numbers themselves. A one-to-one mapping means each image has exactly one pre-image. So if I think of these, the image is the new transformed one. So over to the right, these would be my image. And the pre-image is the original. So a one-to-one mapping means that each image has exactly one pre-image. So if I'm looking at what I see up here, it means each number on the right should come from only one number on the left. And what's actually up here is not a one-to-one mapping, and the reason it's not a one-to-one mapping is right here. The image of 2 actually comes from two different pre-images. So the example up here is not a one-to-one mapping. Transformation is a one-to-one mapping from the whole plane to the whole plane. So it's really taking any given number you have and transferring it to a new location, but each location only comes from one. So each image that you end up at only comes from one pre-image. And the last thing we have is an isometry, which is also sometimes called a congruence mapping, and it's a transformation that maps every segment to a congruent segment. So I can almost think of it back to like the triangle here. If I were to take the triangle and move it somewhere around over here, even if I end up taking this triangle and end up rotating it or sliding it any place else, the triangle is still congruent to the original one. I haven't adjusted any of the angles, I haven't adjusted any of the sizes. If I keep the transformation in that way, it's an isometry. So everything is going to stay congruent. Theorem 14.1. An isometry maps a triangle to a congruent triangle. So if I look up here, if I start with my original triangle, which would be triangle ABC, and I flip it around the green line, I get a new triangle, A prime, B prime, C prime, which is my image, and as long as they are staying congruent, it's an isometry. Corollary 1, an isometry maps an angle to a congruent angle. So if I look over my diagram at the right, angle A is congruent to angle A prime, angle B is congruent to angle B prime, and angle C is going to be congruent to angle C prime. Corollary 2, an isometry maps a polygon to a polygon with the same area. So this deals with any polygon, but I'm just going to look at the triangle over to the side. So if the triangles were congruent, then they should have the same exact areas. So if I took any polygon and made an isometry, it's going to be exactly the same size, so it should have the same area. Number 1. If function f maps x to 3 minus 2x, find the image of 5 and the pre-image of 13. So it's really saying the first one is, what is there if I substitute in a 5, where would I end up? So if I substitute in a 5 in place of x, what do I get? Well, I get 3 minus 2 times a 5, which is 3 minus a 10, which is a -7. So if I start at 5, I should end up at -7. So the image for 5 is -7. Over on the right does the same problem, but in reverse. So it's really saying, what value should I substitute in So that when I substitute in 3 minus 2x, that I actually end up getting a value of 13. Well, now I just solve this equation. So I subtract off 3, you get negative 2x equals 10, divide by negative 2, and x is negative 5. So the pre-image of 13 is negative 5. If you start at negative 5, you'll end up at 13. Number 2, if f of x equals 2x squared minus 1, find f of negative 3 and f of 3, and then is f a one-to-one function? So first off, let's substitute in and see what happens. So if I substitute in a value of 3, I should get 2 times the 3 squared minus 1. Well, first thing I do is square the 3, so I really have 2 times a 9 minus 1, which is 18 minus 1, which is 17. Now let's see what happens if I substitute in negative 3. Well, I'm substituting into the same function, so it should be 2 times negative 3 squared minus 1. Well, negative 3 squared is 9. 2 times 9 is 18. And 18 minus 1 is 17. Now I'm going to look at these together. The first one said if I started at 3, I end up at 17. And the second one was if I start at negative 3, I also end up at 17. So the last part says, is this a one-to-one function? And it's not going to be a one-to-one function because to get 17, it started at 2 different values. It started at 3 and at negative 3. So it's not a one-to-one function. Given the mapping T that maps xy to 2xy, plot the following points and their images. So first I'm just going to start by plotting the points they give me. So m is 0, 0. N is 3, 0. P is 3, 6. And Q is 0, 6. So these are all my pre-images. Now what I'm going to do is I'm going to substitute each of these values into 2x, y. So if I do that, my m prime, which is the answers I get when I substitute in m, I just think of substituting 0 in for x. 0 times 2 is 0. The y value has no change, so that's going to stay 0. Then my n prime, I'm taking the x value, multiplying it by 2, so 3 times 2 is 6, and the y value has no change. Substituting in the p value, so getting p prime. Again, I'm just doubling the x value to 6, the y value has no change. And then q prime, when I substitute in the values for q, again, x value gets multiplied by 2, the y value has no change. So now if I plot these values, I'll plot them in a different color. M prime is 0, 0, so still the same location between m and m prime. N prime is 6, 0. P prime is 6, 6. And Q prime is 0, 6, which happens to be the same place as the Q. Number 4, is MNPQ a square? Well, let's connect MNPQ. So if I connect MNPQ, is that a square? And the answer is no, it's a rectangle. Then if I connect the next one, is M prime, N prime, P prime, Q prime a square? So if I look at it, it looks like it could be. So let's see it. If it goes from 0 to 6 across the bottom and 0 to 6 vertically, all the dimensions are 6, so this one is yes, it's a square. And number 5, is T a transformation? And the answer is going to be yes, it's transferring the location from one place to another. And is it an isometry? Well, to be an isometry, the big thing I remember is it has to keep everything congruent. So if I started with a rectangle and I ended up with a square, all the pieces are not congruent to what they started with. So is it an isometry? No.